you. It is my pleasure to introduce Daniel Luo for his presentation entitled Glycocalyx Engineering of Vascularized Grafts to Achieve Localized Immunomodulation. Daniel Luo is a final year PhD candidate at the University of British Columbia under the supervision of Jayachandran Kazakadathu. Daniel has published on various polymeric biomaterials for therapeutic intervention with teams at UBC and at McMaster's, where at the latter where he completed his Bachelor's of Science under the supervision of Supervisor Todd Port. Daniel?
Thank you so much for the introduction, Java, and thank you, CDTRP, for allowing me to speak on this subject today. So to begin, you guys are probably very familiar with what this schematic is trying to convey. So we have a recipient, we have a donor, somebody needs an organ. The organ is going to exist outside of the body for a period of time before it's going to be put back into the body. In our lab, what we're interested in is the glycocalyx, which is a structure found atop the blood vessel lumen. This is a carbohydrate-rich layer found on top of the endothelial cells, containing glycoproteins, proteoglycans that do a lot of the work that we really needed to do in the immune system. So a healthy glycocalyx is going to modulate immune response. It's going to allow for cell-to-cell communication in such a way that it's healthy, but also it is a large structure that really just fortifies the endothelium to create a sieve-like barrier to allow appropriate nutrients to diffuse through. Now, during the process of organ procurement, there's going to be different fluids, organ preservation fluids coming in and out, blood coming in, different temperatures, and through sheer stress, as well as biological differences of the donor and recipient, we're going to see the damage of this blood vessel. So the glycocalyx is going to be shut off. And when that happens, we see propagation of inflammation, we see immune activation, and also this sieve-like barrier is gone. And so there's a lot of a leaky channel within the endothelium. And so this is one aspect we see that does require some sort of targeted therapy within a transplant setting. And so we decided to do a targeted localized approach to mitigate this problem. How we thought about doing this is basically creating a polymer coating on top of the blood vessel that is going to be introduced during the procurement process. So we would just dope it into the organ preservation solution and hopefully paint on top of the blood vessel of the organ. So our design needs to work in such a way that it recapitulates the functions of the glycocalyx as well as it fortifies its structure. Here is the structure that we came up with, and don't worry, you don't have to be a chemist to understand it. I color-coded it for you a little bit. So in the yellow, we have a peptide sequence, and this is used for an enzymatic approach to decorate and immobilize these polymers on the blood vessel surface. So they're anchored and they're localized just to the organ. The blue is a polymer, polyglycerol, and this allows for a large brush-like structure to recapitulate some of the structural functions of the glycocalyx. And then lastly is this sugar structure in purple, the sialic acid. So sialic acid sometimes is deemed as a self-ligand. It allows immune cells to recognize that ligand and say, okay, this is my own tissue, I should not attack it. And so it deactivates immune activation of the cell. And also, actually, what happens is that in cancer cells, they have upregulation of sialic acid. And a lot of the time, it has been shown that these sialic acids are actually one of the mechanisms they're using to evade the immune system and then grow and become, detrimental to the body. So doing that, we first began looking into it in vitro using an endothelial cell line model using EHY cells. First, we looked at it under confocal to see that it is in fact being decorated on the cell surface. So with the confocal image, red is the cell membrane, yellow being the polymers. And then we saw that it is a transient coating. So it has a half-life of 8 hours. And so within a week, everything is being shed off and it is temporary. It is not a permanent modification. Then we looked at whether it is in fact going to create a immunoevasive coating. So under inflammatory conditions using TNF-alpha, we saw that in the presence of our polymer, we were able to reduce the interaction of immune cells isolated from blood. So in this case, we stained the immune cells with fluorescent dye, and we saw that there was a lowering of this fluorescence. But also with that in mind, without as much recognition, we also then saw a lowering of immune cell-mediated endothelial cell death. And what I wanted to bring your attention to at the bottom right graph, that's a test with HLA-A2 positive CAR-T cells with endothelial cells that are either modified or unmodified. And in the red line, that's an unmodified endothelial cells. Then when we see the blue line, that is a polymer modified cell without any sialic acid, and it is reducing the cell death. But we noticed that including the sialic acid into that polymer, we even further decrease the amount of cell death experience. So the sialic acid is doing some sort of work there beyond just the polymeric structure itself. So having this preliminary results, we decided to get a collaboration going with Dr. Jonathan Choi at SFU to look at this model using an aortic interpositioning model and through an allogeneic mice transplant. So what we did is we took a piece of artery from a donor mice, took it out, flushed the blood out, either incubated in UW solution, which is an organ preservation solution, or UW solution doped with our cell surface engineering molecules. And then for 1 hour, static cold storage, and then flush it all out before we transplanted it into a allogeneic recipient mouse. We tested it under 3 time points, day 2, day 15, and day 42, to see different time progressions of the damage and to see if we were able to have any difference in the prevention of any sort of rejection score or tissue damage because this is a transient coating. So what we did is then went through different types of scoring. So for day 2, we did medial thickness. We also did grading for leukocyte infiltration and tissue damage. Then at day 15, we did rejection scoring, which is a collection of different grades based on leukocyte infiltration, medial thickness, and then also fibrin deposition, et cetera, to come up with a rejection scoring to see how bad the piece of tissue is rejecting. And then at day 42, we did luminal narrowing compared to native artery tissue pieces. And through all 3 time points, we noticed that the presence of this polymer was able to improve the characteristics of the tissue after the transplant. So we saw that this was really promising, but also looking at the plasma when we were testing it, at day 2, we saw that the cytokine levels for pro-inflammatory response as well as IF and gamma signaling was decreased in the treated arm. And then also IL-10 for a anti-inflammatory response was increased in the treated arm. So that was really promising to see. But then also looking at it at day 42, we saw that there was a lowering of de novo generation of donor-specific antibodies. And this is really interesting because, like I mentioned before, it's a transient coating. Theoretically speaking, it should all be gone and out of the body within the first week. But we are seeing effects long-term. So that's very exciting for us. And it's a one avenue we are going to be looking more deeply into the mechanism of how this polymer and how sialic acid is affecting a short-term effect physically, but then a long-term response in the body. But with that in mind, I've been trying to say Glycocalyx engineering. And the idea of Glycocalyx engineering isn't just because the Glycocalyx is damaged, but we really wanted to take this opportunity to make it so that it is in fact localized. It is not a secret that immunosuppressants are global immunosuppressants are affecting the body. And though they are helping the organ health, they're not necessarily the most friendly to the body. The immune system is being shut down, and so the quality of life is affected for the patient. And so we wanted to make sure that it was sticking just purely to organ treated. In this case, what we decided to do is do a double transplant. So the first transplant, still the same as previously. We're using a piece of artery, we're transplanting allogeneically, and then waiting for 28 days. And we're doing a second transplant, in this case, a skin graft. We decided to do 3 different pieces of skin, one that is similar to the donor, one that is similar to the recipient, and one that is a third-party skin graft that is not a strain of either the recipient or the donor. And we saw that the rejection of the skin was similar in both the treated and untreated arm of mice, meaning that the effect of the modification on the artery had no non-specific effect down at another part of the body, particularly in this case, the skin. So that was really promising to kind of show a localized effect. And so with that, a very small vignette snapshot of what we've been working on, that glycocalyx engineering could be an avenue moving forward for cell surface engineering to really tackle some of the problems that organ transplants might face. And so because this is synthetic, we see polymer design that can be really interchanged and for different targeted effects. And in future, like I mentioned before, we are going to be looking at mechanism of action as well as more additional small animal models that could be more clinically relevant readouts as well as an immunosuppression comparison. So obviously, this work cannot be done by one person. It takes a whole village. So I would like to thank all the faces and all the funding agencies and the screen, as well as all the background partners that might not be on the screen as well. And I'll take any questions you might have.
Thank you so much. So I'm going to use a little bit of my immunology background to ask this question. I don't know if it'll be good, but so you looked at de novo antibodies at day 42 in the tissue. You did immunofluorescence.
In
correct?
plasma.
Sorry, in plasma. Okay. So do you think since sialic acid can have this immune escape mechanism, are you going to be looking at that in the blood long term for potentially like any cancer effects? Like, do you think that could have any effects long term since you are seeing?
Right. So you're like trying to think of linking, if we're hypersialating this piece of tissue, is it going to be acting similarly to cancer cells in a negative manner?
Yes. So is it going to have a negative effect if you did use this in humans?
Right.
Will this have immune escape mechanisms since you are seeing the positive effects for transplant long term in the blood?
Right. Well, we are not fully sure on the elucidated mechanism, or we haven't elucidated the full mechanism yet. We're thinking it is a sialic-based mechanism because of sialic acid to reduce NK cell activation. That's what we're thinking. In terms of whether it's going to be having cancerous effects, not too sure yet. However, the different snippets of data that we have in terms of it being transient, but also having long-lasting effect. We don't know where that effect is stemming from, whether the DSA generation is happening during while the polymer is still present, or is this after the polymer has already escaped from the body and it's some sort of downstream effect that it might be a different mechanism causing it. So we don't know if it's a direct effect.
Okay.
Yeah,
Thank
sorry.
you.
Danielle, can you also comment on so I've forgotten exactly the timing, but you had elicited the implants elicited DSA. Did you look in the grafts at whether the DSA was actually causing damage to the graft? In other words, it seemed to be able to stimulate the production of antibodies. Did those antibodies, was the graft protected from damage from those antibodies?
No. So you're asking if we looked, because the DSA, yeah, so the DSA data comes from the plasma itself, but in terms of the graft, day 42 graft data, that was what we reported here is purely the intimal thickening, the amount of swelling that had happened and how much healing there was. So we didn't actually score or looked at the features of the histology based on the antibody.
So I'm just wondering if the protective effects on the graft itself, for the graft itself, even though the polymer is presumably gone by that time, was there still some kind of protection from the damage of the antibodies that were elicited by exposure to the alloantigens?
No, that's a good question. We haven't directly looked at it, and that'd be a very good one to see, just because our hypothesis is that if we can nip it in the bud from time 0, it presumably has a long-term effect, and that's what's happening. But that would be a good avenue to look at.
Interesting. Francois?
So thank you for the presentation. So I was wondering, you look at the assay, have you looked also to the autoantibodies production in this model?
No, we haven't looked at that specifically. We just purely looked at the DSA. Actually, after doing the experiments, it was kind of revealing or surprising for us to see. We weren't really expecting this piece of data to come out the way that it did. But that'd be a good thing to look at.
Thank you.
Last question.
Very nice work.
Thank
You might consider giving MR1 or some other antibody to to additionally attenuate the alloimmune response. I think you'd be able to show that relative to conventional immunosuppression, this may be protective in a way that would be clinically useful in that
Right.
context. Because obviously, once your glycocalyx is worn off, the immune response is going to happen, and that's what you're measuring with the DSA. But I would guess that if you recalibrated the model with a couple of doses of MR1, I think is a standard thing for this model. That would be
Right. Oh, no, that's very good advice. Yeah, all these transplants were done without immunosuppression. So we are looking into a kidney transplant model that is amenable to immunosuppression in rats. So that would be very revealing for us.
And with respect to the prior question, Vimentin is an easy autoantibody to look at that should be positive in this model.
Perfect. Thank you so much.
Great. Thanks very much.